Well, good day everybody. We are discussing about information, and so far we have defined what is mutual information, uh, and we are discussing about the specific example of a binary symmetric channel. This is a popular model, simple model, which is used many times to bring out different important issues and features in the design of digital communication system, viewed from an information theoretic approach. So, this is the channel. We will continue discussing for some more time as an example. In fact, in our last class we tried to calculate the mutual information for two different categories of event. One was of the type x1 y1 x2 y2, okay, and we found that I x y in that case had an expression like this: log 2 1 minus epsilon, base is always 2 as usual, and we should also make it a practice to note the unit bit, okay. And then the other kind of mutual information when x1 is transmitted, but y2 is received, which we know is an event of error. Maybe binary 1 was transmitted, but 0 was received. Similarly, as if 0 was transmitted and 1 was received, the corresponding expression for the mutual information turned out to be log of twice epsilon. Okay, and we were discussing about the various values of epsilon that may be considered, and we found that epsilon equal to 0 means that the channel, binarily symmetric channel, is noiseless. It is an ideal channel really. Epsilon is the transition probability, is a noiseless channel, and hence we can say that the output of the channel determines the input to the channel, or something like that. Little bit of interpretation will bring out this issue. So, we move on. The next interesting case is, I guess we did not touch upon this point, the specific value of epsilon is equal to half. What is this? What does it mean really? We can see from the earlier expressions that I x1 y1 or I x2 y1 both are 0. That means you do not get any information if the channel transition probability is half, okay, then you do not get any new information irrespective of what was transmitted and what was received. This is equivalent to saying that as if there was no channel, or if I had to communicate some information from source to a distant place called destination, I actually need not have transmitted it through a communication system. What I could do is that for this binary situation, I could toss a coin at the receiver end and could accept the outcomes as head or tails as my possible received bit stream, and that would be the same as the actual transmission system really, with a transition error of half. This simply means that as if the channel is totally noisy, so much so that the errors are very random, okay. The error probability is maximum of half. I say the maximum error probability or channel transition probability is half. Do not think that the maximum value of epsilon is 1. If it is 1, which means that we know that all the bits are received in error, and by using a simple inverter I can correct all the bits. So, that is equivalent to noiseless transmission really. So, the most severe situation in terms of this information theory language to describe a physical channel perhaps would be that the channel transition probability epsilon is 0.5, okay, which means that it is something like the most noisy channel, okay, and so noisy that there was no point in transmitting information through the system, through a communication system really. There was no need for designing a system as such perhaps. Anyway, so this is ultimately an ideal situation. No practical channel is so bad really. In fact, no system designer would ever envisage a channel so bad as this really. So, the values of interest for us for epsilon will be anywhere in between 0 and half. Usually for a given channel, when only the propagation channel is given to you, you can expect that the resultant or the corresponding epsilon will be much less than half, much less than 0.5. And in that case, let us see whether our mutual information gives us some basis of what kind of action should be taken in general in any information theoretic receiver. To take up, we can say that I x y for x1 y1 when x1 is transmitted and y1 is received, or for the other case of x2 is transmitted and y2 is received, we know that the mutual information value now specifically is about 1 bit. When epsilon is very small, much smaller than 0.5, we can approximate this to about 1 bit, epsilon being very small, not 0, because that is an ideal situation, no noise situation, but is close to 0. Okay. In fact, I indicated earlier that a typical value when you do not know anything about the channel, and if you are trying to guess the channel transition probability for usual communication systems of point to point wireless and even telephone lines systems, you may assume that epsilon value is of the order of 10 to the power minus 3, okay, 0.001 or say 0.01 kind of thing. 0.01 is quite noisy channel that way. So, for such low values of epsilon close to 0, one can approximate and see that this mutual information for this category of transition is about 1 bit. Whereas, what happens to the other kind of mutual information when x2 was transmitted and by error y1 was received, or x2 was x1 was transmitted, y2 was received in error, we can see that the corresponding value of mutual information becomes less than 1 bit definitely, and it becomes negative even. Okay. And somebody rightly pointed out some time back that yes, mutual information may be negative. Here is an example where the mutual information value is even negative, which by common sense means that you do not gain any information when this kind of error occurs in the channel. Okay. Whereas, when there is no error, you gain in information, and how much is this information gain? 1 bit for transition of 1 bit. So, 1 bit was transmitted, okay, error probability was very small, error transition probability, and as a result I can see that the mutual information offered by the channel is also close to 1 bit really. Okay. So, if I have some a priori idea about this mutual information, knowing the channel behavior in terms of its transition probabilities, I can use this information, mutual information measure as my design criteria for designing the subsequent system. I could even say that for those cases when the mutual information is positive and very high, I can guess, I can make a receiver decision as if that decide y equal to y1 for this first case. If I have measured, so 1 bit has been transmitted, I have received that bit, and I somehow have found that the corresponding mutual information x1 y1 was close to 1 bit. From this knowledge, I can even guess that for y equal to y1 at the output channel means that it is highly likely that x1 was transmitted, and that is what is the decision making process in the receiver. Okay. And that in some cases, in a hypothetical situation, that is the end of decision mechanism in the receiver, and we can give out this data to an information source, an information sink in the receiver end. So, these are hypothetical example, but still it brings out some feature about how one can think of designing the receiver, and it will gradually be clearer that designing the receiver is much more complicated, much more involved issue compared to the design of the corresponding transmitter block, at least in most of the cases. And when I get a mutual information which is 0 or close to 0, much less than the earlier mutual information or even negative, we say that okay, there was an error perhaps, and it is very unlikely that x2 was transmitted. Okay. So, by default for this binary situation, we could also guess from this inference that well, x1 was most likely event that had occurred at the input to the channel. Yes, please, any question?
Sir, like it's highly unlikely that x2 was transmitted, then actually we have gained information about x2 also, like whether x2 was occurred or not.
Yeah, that is the merit of mutual information. You now guess by seeing y1, you now have some idea about how probable x2 was at the input. That is what is being stated in this simple language, that well, it was highly unlikely that x2 was transmitted.
So, like information is less than 0, still I have got some information about that.
In fact, you have got see, what he says is that you have got information about x2. Yes, that is what you have got really.
So, like what is the point of saying that it is less than 0? Still I have got.
But this information you got, okay, only after observing y equal to y1, and please note that for y equal to y1 the probability was high, half. That is how the mutual information became negative. If we just go back to the earlier expression and try to find out, I mean, why this became negative really, you will find that in the basic expression for mutual information there is a conditional probability at the numerator. It is because of that basically. Do you get me? So, value wise it may be negative or positive. In fact, you can say that yes, I have got some information, but the information is not a gain basically. I cannot say, I mean, by see if the earlier other information of I x1 y1 was not there. If you had only this information of I xy x2 semicolon y1,
So in this case, this is a binary system. So
right.
I know that if x2 is not other than x1 has occurred.
So you are essentially making a better guess about x1. So these two statements, they are actually indicating the same event. The first statement directly says that x1 was most likely, the second statement says that x2 was much less likely, which means for this binary case that yes, then x1 was likely, because something was transmitted and I have received y1. Okay, the interpretation is different. So both the values, they indicate to the same thing. Okay.
How is it that in one state we are saying we are gaining information, in the other we are saying that there is
This gaining is a colloquial term really. We use the word once when we said that okay, by our intuitive approach really, we would like to gain information and we would like to see information as per our expression to be positive in that case really. Do you get me? So when information is positive, we said yes, we have gained information about x1 over here. When information is negative, this does not give me an additional idea about x2 happening independently really, because fundamentally there has been error. The mutual information about x2 after observing y1 is dependent on epsilon so directly. So we really have not got a unique, more information about x2 so far. In fact, whatever we could have got has been jeopardized by this error probability in the process, because this mutual information for the second case is simply twice of epsilon of log. It is not 1 minus epsilon type as it was for the first mutual information expression.
So in the latter
So
case, since the error is governing our definition of whether the error is strongly governing the factor of our
error is strongly governing the sign of mutual information at the channel.
Let's say that it's probably we're gaining, we're not gaining anything.
You may not gain, you may try to gain, but you may lose, you may not gain information really. Zero information is equivalent to negative information. We can say that we do not get much information about x2 because of this additional undesired uncertainty. When I was talking about undesired uncertainty, I was trying to mean this, that you tried to convey information, something undesired happens in the process, so that you get confused to some extent at the receiver end. Okay. For this simple binary case, confusion about x2 means x1 was transmitted. It was simple, but if there were more than two possibilities, it would not lead directly to one possibility, and that would had to be resolved by some other specific means really. Okay. So those are the issues which have to be addressed in the full design of the receiver, okay, and part of the discrete channel as well. Yes.
Seeing that zero information, getting a value zero does not convey any information. Yes, sir. And negative.
Zero and negative also, let us say, we can include.
The more negative we get, the more certain we are that x2 was not transmitted.
Yes.
So in a way, it is conveying information.
So
Valuable information.
For x1, it will be the more positive. For
just keep in mind that you are talking about a situation where epsilon means that there is an error. Any transition, any change when x2 was not c at the receiver end, your point is that if I have to know whether x2 was transmitted, okay, that's fine really, but things may get changed because of this non-zero value of epsilon here. Okay. So yes, in this binary case, if you know more certainly that x2 was not transmitted, it is equivalent to saying that you are getting more information about x1 as well really. So for this binary case, all aspects of negative information, they are not becoming apparent here. So for this case at least, we can accept that zero and negative information, they are conveying the same thing basically. Okay, it's as good as no information about whether the error occurred over there. Okay. The point is that we can expand this model from a binary to a non-binary channel models, etc. In fact, there are other channel models where instead of considering two possible outputs, while two possible inputs may be there, x1 and x2, one can also bring in the idea of what is known as erasure, some undefined one. Depending on the value of epsilon, when epsilon is not very small, is say of the order of 0.1, 0.15 kind of thing, then you may not like to take any kind of decision. Okay, because this value will not be close to 1, it will be smaller. This value also will be somewhat negative, not very much negative. Okay, and you may like to avoid taking any decision about the received symbol and what was transmitted at the transmitter. So in such cases, there is an idea of bringing in the concept of eraser. You can erase it, hoping that you can also ask the transmitter somehow to retransmit and do something else really. Okay. So, this simple channel model can be expanded in many ways really, but this model is a simpler one. Yeah.
So even if the case is not binary but multiple inputs, like multiple states,
Multiple input, multiple outputs. Yeah.
so even in that case, if I know that something is very the information gained about some x1
For some
y
mutual information for one case
is very much less than 0, then I'm very much more confident about that value is not occurring.
provided the corresponding epsilon value is very small. When the epsilon value is, see, the end result may be negative because of many factors really, the input probability of the symbols and other things, input probability of x1, x2, etc. So, only the end value, if you are comparing only the end value of mutual information, best thing is to compare. You may have cases where if only one positive value of mutual information you have got, for 2, 3 you have got negative values. Then amongst these 3 negative values, the one which is least in the lowest one in magnitude, I mean you can accept this to be more reliable kind of thing.
So what I want to say is that if it is less than 0, then also if it is the absolute value is actually governing the amount of information I am getting.
No, the absolute value does not govern.
If I am getting much more less than 0, then that means that I am confident about much confident about that thing did not occur, so I can concentrate on the other states.
That is because of that is very specific for this example, where we assume that input symbols are equally likely and there are 2 possible symbols. Okay, that is more specific to this example. I shall try to bring out one more example maybe in the tutorial class, where we will find that neither the negative magnitude nor the negative value nor the magnitude of that really gives you, so long as it is 0 or negative really, it may not be useful, it may not be reliable really, especially when you have got for other situations positive information values. Okay. So, and this problem is for mutual information for a certain events only. Okay. What is more important in the design of systems like your source coder, channel coder, are some average value of information, average value of mutual information, etc. We will define that. Okay. That characterizes the overall behavior of channel, in some cases overall behavior of sources. Okay. Now, we define self information. Please go through this quickly and tell me whether we have defined it already. It is almost self explanatory. I am trying to define a new term called self information, okay, as a special case of mutual information. What I am assuming is that we can see if the numerator here is 1, this conditional probability is 1, then we get a familiar form which we have encountered earlier. When the numerator is 1, this mutual information now looks like log of 1 upon p of x k. And when we talked about quantifying information, we use this expression, is it not? So, we can say that this information, which is a special case of mutual information, defines, I mean gives us an idea about the information of an event x equal to x k. Okay. And this kind of information can be defined over one ensemble x also, because in the context of a joint ensemble, the other ensemble, I mean it always specifies, say occurrence of y equal to y j implies that x equal to x k has occurred. This, that is the meaning of this conditional probability being 1. P of x k given y j is 1. That means if y j happens, I know that x k has happened. Okay. And in that case, we as if get a single ensemble consisting of x only, and the corresponding average, corresponding mutual information simplifies to or reduces to what we earlier saw as a information associated with an event defined over a single ensemble. Okay. We now call this as self information. self information. Earlier we did not call it as self information. Now let us, from now onwards, let us call this as self information, which is a special form of mutual information when this conditional probability in the numerator is 1. Okay. And we can see that we can now say self information is a form of mutual information which can be defined over one ensemble, and when the conditional probability value in the numerator is 1. Okay. And again I can say that the self information value is non-negative as my original information was. Only for mutual information things became negative in between perhaps. We have defined mutual information, we just now defined self information. Let us think of averaging this information. Okay. There is a parameter, very important one, which is called as average mutual information. Okay. Note down this expression and tell me what kind of averaging has been done. Averaging, as I understand, can be done in many ways. We are still talking about a discrete ensemble, joint ensemble x y. Okay. And is this expression different from the earlier expression of mutual information?
It's just a summation.
Summation of?
There is no difference, but there is a summation of all the values, all the combinations.
It is not just summation of all the mutual information, and weightage is by what kind of probability? Joint probability, is it not? And that is how we can say that yes, this is an averaging operation, it is a statistical averaging operation, is not it? So, averaged over the full statistical experiment, which is the joint ensemble really. Okay. So, if I go on observing the outcomes of that joint experiment, all possibilities with their and then come out with the possibility, probability of each event there, and then come out with an average value, I get this. This is a mathematical form of that, and that is what I am calling as the average mutual information. Note the difference in notation now. Average mutual information, I am indicating not in terms of xk, xi or yk. I am simply showing the ensembles capital X separated by colon from capital Y, because once I have done this averaging operation, this parameter now is not dependent on only one event. This parameter depends on all the events with their respective probabilities. Okay. Yes. Well, this average mutual information gives you an overall idea in some sense about the whole, about the joint ensemble. Now, if you try to map it onto a physical situation and say that okay, some statistical experiment is occurring, then my simple point is that you cannot come out with this averaging operation unless the whole experiment is complete. It has produced all possible outcomes with all probabilities. So, if you try to mimic and try to get this kind of average mutual information value from an occurring experiment, you should observe for a sufficiently long period. Okay. But this parameter is important in the context of information theory and signal, coding, because the very famous theorem by Shannon, Claude Shannon, relates this average mutual information of a channel like this binary symmetric channel I showed, of some channel, discrete memoryless channel DMC, and he defines a very important parameter called as the capacity of a channel. Capacity of a channel. This capacity word, we use many a times really, but he has defined in a very quantitative manner. In fact, we will not discuss much about that channel capacity and its implication. Maybe towards the end, if you have some time, we will come back to evaluating the capacity expression for a special kind of waveform channel for continuous input, continuous output channel. But let me tell you that Shannon, what he found and established mathematically is that for a channel, discrete memoryless channel, the maximum possible value of this average mutual information he called as the capacity of the channel. Maximum value, maximum possible value of this average mutual information. Okay, he called as the capacity of the channel. This process of maximization is a bit complex to understand at this moment. Now, see the way it is I have introduced here, this average mutual information is over the entire ensemble. Okay, I am not talking about any maximization over here. Pardon? Sorry. Once you define your individual ensembles or the alphabets and the probabilities, okay, this will come out with a single value. Okay, so average mutual information should be a value and the unit should be bit. What Shannon established, okay, ultimately is that if you do some kind of maximization operation over this parameter of average mutual information, maximization in terms of the input source symbol probabilities, the first ensemble X, if you think of all possible probabilities for the source letters x1, x2, x up to x capital K, and which will result in different values of mutual information. If well, I do not have the diagram today really. If you imagine that same noisy channel block where the input alphabet is from x1 to xk and the output alphabet is y1 to yj, what Shannon established is that if the input probabilities of this xi's, they can be varied to all possible ranges, and then for every set of values of this probability come out with average mutual information, you get one unique value. And if you pick the maximum value of that average mutual information for a particular probability distribution at the input, then that maximum value of average mutual information is no more dependent on the input probabilities. What is left in that maximum average mutual information is something which only is related to the channel behavior, and that is how he called it as the capacity, channel capacity. It is a bit complicated. I mean, it needs some more theory really to establish this point.
Yeah. Does it depend on how we are setting up the ensemble X and the coding ensemble Y?
How the two ensembles are really, yes, so far as this is concerned, yes, it does depend. If you change the probabilities of the input and output, this value will change. You are correct. Okay.
Capacity is something beyond which you can't get information.
It's that's the next part of his famous theorem really. First he established the capacity definition of a channel. It's the capacity of a channel. Okay, that means when this maximization operation is done, it is no more related to the source behavior, and it is now a property of the Y ensemble as if, okay, which is the channel. And then he says very interestingly, and he proved also, that one should not think of conveying information at a rate more than this capacity offered by a channel. Information can be conveyed through a channel, noisy channel, so long as the information transfer rate is less than the capacity of the channel. Okay. It was established that if somebody tries to convey more information than the capacity of a channel, okay, then there may not be enough control in whatever output you will be getting. You cannot control the errors, okay, and things may go very bad even. That is a possibility. Whereas he again showed that if you decide to transmit information at a rate less than the capacity of the channel, then by using some techniques of error control coding, etc., you can always bring down your error rate, error probability of error at the final information sink. If you want to bring down your error rate to a very small value of 10 to the power minus 12, should be possible. Okay. If you want to adjust it to some intermediate value of 10 to the power minus 5, is very much possible with a less complicated circuitry, etc. So what he assured for the first time is that when the information transmission is at a rate less than the capacity of a channel, it is possible to ensure almost errorless transmission, which implies that one can transmit with as low probability of error as he wishes. He has to pay the penalty in terms of complexity, etc., somewhere, but it is possible ultimately. Whereas if the transmission rate of information is more than the capacity, then there is no guarantee. That was a very famous development in the late 40s and early 50s in the last century. In fact, that led to a lot of activities in the areas of error control coding, design of digital systems, digital receivers, etc. And it is still a very fundamental and key guide to the design of digital communication systems, but we will not go much in that. Yes, please.
How does the concept of rate time?
Yeah. It's in fact capacity. See here, the information, the mutual information, average mutual information unit is in bit. Okay, we can map it to some information per second. We can normalize it to saying that, okay, so if I transmit, if my information transfer rate is 1 bit per second, the time dimension can be brought in easily by extending this idea. Think a little bit. I mean, if we won't go into that basically, I mean, that will again take some 2-3 lectures hour really. We'll try to save that. If we get some time towards the end, we'll get back to this issue in more detail. Okay. So averaging is carried out over the joint ensemble XY. So this mutual average mutual information is not dependent on one specific outcome. You should calculate the average mutual information expression for the binary symmetric channel, you know, okay, and you can also like to sketch how the value changes with epsilon. Okay. One assuring thing is that this average mutual information is non-negative. This is not negative really. Okay. So capacity of a channel is never negative. As simple as that. A channel has got a capacity 0 plus, in some cases 0 if there is a total barrier, nothing can go, that is 0 capacity channel. Okay. This equality, this Ixy is equal to 0 with equality holding if and if x and y are statistically independent. That means whatever symbols are being generated, it is no way influencing what you are getting. Okay. Like if you like, one example is that, I mean, you have got some data, some kind of PN sequence you have generated in the lab, you are trying to transmit through a fluctuating LED. Some LED is switching on and off to indicate ones and zeros, and you have put an obstruction in between. So nothing reaches, no light reaches at the receiver end, detector end. So the detector output is not at all dependent. So the information for this channel with a barrier in between is 0 really. Okay. If you had an wire and the wire has snapped, so it is a 0 capacity channel, because the input and outputs, they are independent. Okay. But otherwise the channel will have a capacity. Well, so we defined averaging of mutual information. Should there be some kind of parameter averaging the self information? Yes, why not? Okay. So there is a parameter known as entropy. Entropy is already known to you, must have been discussed in the context of thermodynamics or some other subject. Okay. The name is derived from there only. Okay. And entropy is nothing but the averaging of the self information over its own ensemble, and hence the expression is very easy to write. If you remember the general expression for statistical averaging and the fundamental expression for information, you can on your own write the expression for entropy really. Summation of Pxi log 1 upon Pxi, or minus summation Pxi log Pxi, unit is the same bit, okay, with a base of 2. So entropy can be defined over one ensemble, whereas average mutual information needs a joint ensemble. Okay. Now there are several theorems, again we will not get into, but I thought I will just mention one of them really, which may be of some importance if you think subsequently after we discuss about some source coding technique. One theorem says that if I have got k possibilities x1 to xk, capital K, okay, then the entropy of that ensemble h of x, the average value, should be less than equal to log of k, less than equal to log of k. This point I am noting really. I mean, there are several theorems. Okay, one of the fundamental ones says that if you have k possibilities or k possible outcomes from that experiment, which is indicated by the ensemble capital X, then it can be shown that h of x is less than log of k to the base 2. Okay, and this equality holds, that means h of x is equal to log of k when the elements are equiprobable. Like in our binary symmetric channel, at the input I can define as ensemble x, and we assume that let x1 probability of x1 be equal to half, be equal to probability of x2. Okay. So, for those cases really the ensemble, the average entropy or the average value of self information or the entropy was equal to log of k. K was 2 in that case really. So, it was 1 bit really, the entropy was also 1 bit. So, when the elements are equally probable, by elements you remember I have defined elements earlier really, elements are the outcomes basically, okay, from the statistical experiment. When the elements are equiprobable, then h of x is equal to log of k, otherwise it is less than that. H of x, now let me ask, is it a characteristic feature of a source, information source? Let me recap. Average mutual information, which I defined some time back, may be viewed as a characteristic feature of a channel and the source taken together, because it is defined over a joint ensemble. Okay. There has been a famous theorem defining a capacity of a channel and relating it to information rate. That capacity is a special form of average mutual information, wherein the capacity is made independent of the ensemble X, so that it is a feature of the channel itself, but we said we will not go much into that really. Now, I am talking about self information and its averaging one, wherein we have got an entropy which is defined over one ensemble. Now, if I think of this ensemble X as being the output, okay, as that of a source, discrete source or information source, the way we have defined, can I say that entropy, this parameter can be used to characterize a source, information source? Okay, it is defined over one ensemble, and this ensemble X I can relate to the information source. Okay. So, if the source output has got k number of possibilities, I can find what is the entropy of the source. So, entropy of a source is a meaningful word now, is a meaningful thing you may like to pursue. You may like to say that okay, this source has got this much of entropy, a different kind of information source may have different kind of entropy. That is a valid point. Okay. Now, one just question here, which means I won't like to discuss to save time really, is that if you get back to the basic expression of mutual information, okay, we know that it consists of two ratio of true probabilities, log of that really. The numerator probability was a conditional probability, and we are defining self information and entropy, these two parameters, based on the probability p of xk, which was in the denominator, assuming that the conditional probability value was 1. That is how we derived self information from mutual information. You should not stop there really, you can think then why not I assume that p of xk is 1 and I define some kind of conditional self information, continuing with the conditional probability at the numerator. So, I can define a conditional self information as log of p of yes xk given yj kind of thing, okay, as a special case of mutual information, once again assuming that p of xk is equal to 1. It is possible theoretically, okay, and these are defined.
We had said that we won't be considering p of xk equal to 1 in. So, in that few slides you had said that we won't be considering.
But you didn't object. You didn't object when I said let the conditional probability be 1. You should have objected. The point is that when I am saying that okay, the conditional probability is 1, I am doing it for all values of I and j. Is it not? And by that I am identifying, this is actually for understanding, I am identifying that okay, one ensemble is not important now really. If something happens at y equal to yj, that means the other outcome was known for certainty. Okay. We exclude an individual event with a probability of 1 only, because that may lead to problems or probability of 0. So, this we decide that at the beginning. So, when you have a situation where there is a joint ensemble, but the probability of conditional probability is 1, you do not consider it for further discussion. So, the focus is on the residual or the single ensemble of x or y as it may be. So, proceed with that. Okay. So, for understanding I am assuming, and that probability is 1 for all possibilities of I and j really. So, I mean start with a common definition and bring out different possibilities. So, one can define a conditional self information and ultimately by averaging statistical averaging something called conditional entropy. Okay. So, I would like you to think a little bit, come out with the expression, so that we can discuss if it comes to that about the expressions etc.
Specific. I mean, other than being which of the source, like I know a source has this much entropy.
Right.
So beyond that, does it
It has an implication. It has an implication really. Okay. In fact, just very big, and we have a brief idea about that. It is important to assess the entropy of a source, because that gives you entropy. I can also interpret as the average amount of information which is coming out. Now, if I again try to relate this source output with time, So, with every unit of time how much of information is coming out from the source, and if I say that okay, one letter is coming from the source at in 1 second or in unit time, then I can say I have got hx bit of information per unit time. Can I not say that? See, I am saying that let my letter rate from the source be 1 letter or 1 symbol per second. I am normalizing the time scale. Then I say that if the source has got an entropy of hx bits, then per symbol or per letter I am getting hx bits. Do you object?
Per second you are getting.
And I am getting 1 letter per second, okay, and 1 letter on an average carries hx bit of information. So I say as if I am getting hx amount of hx bits of information per second, okay. So it's possible, yes, and this information is useful, is exploited for designing the source coder, okay. Well, so yes, this is this kind of visualization of a source is important and useful. Now, all this was the introductory definitions and basic ideas about certain parameters which play important role in information theory and coding. We will now settle down quickly to get some idea about discrete source coding operation. And as I said, our discussion on source coding and channel coding will be very brief. Our main issues are elsewhere. Okay. So, I will have one specific example of source coding technique, bringing out why source coding is attractive really. We know the overall aim of a source coding to reduce the bit rate, etc. We will take up Huffman coding, okay, maybe in the next class. To prepare the background, let me say that the source that we have been considering were discrete sources so far, is it not? Okay. In fact, we are also implying that the source also does not have memory perhaps, though it was not explicit. I did not discuss much about that really. At least from this point onwards, let me consider that the source that we will be talking about is a discrete source and memoryless source. What do you mean by, what do you understand by memoryless source? We discussed about memoryless channel. So, can we just use the idea and try to define what we understand by a memoryless source? The source is generating x1, x2 like that, these letters of the alphabet, capital of the source alphabet, okay, and I am saying that let the source be memoryless. So, or the letters generated previously, yes, that is it. The occurrence of a letter at the output of the source x1 or x2 or x3 is not at all biased or influenced by what has occurred earlier in time, isn't it? Okay. So,
I mean it is incapable of sending a repeat, acting on a repeat request.
No, let you, I mean, if you are using a repeat request algorithm downstream, okay, what you do is that store this letter which you are going to transmit somewhere else in a buffer, but do not allow this stored xi to meddle in the generation of the next symbol. Fine, no conflict as such. So, you can still go for ARQ system really for a memoryless source, okay, because the next symbol is the current symbol is not being allowed, or it does not do it naturally for in the occurrence of influence the occurrence of the next symbol really. Okay. So, there is no conflict with ARQ transmission in that. Is that okay? So, let us consider a discrete memoryless source. So, I mean if I indicate the source output, I can indicate as x1, comma x2, comma etc. up to x capital K. So, k number of possible letters, okay, one at a time with their respective probabilities, and then in the source coding what is done is each letter, the way we have understood so far, is converted into what is popularly known as a code word. That means you code each letter, the letters were defined conceptually, okay. Now, in the source coder you should try to give it a specific form, and one popular form is to represent it in a form of a code word. And again, the most popular way of representing it may be that you represent it in binary bit string, okay, so that we can say that each letter may be represented in a binary code word form. So, we convert each source letter into a code word, usually binary, for at least let us consider binary for our understanding, and see that it is not necessary that we assign same length binary code word for all the letters. That means, this code word generation from the letters may have various lengths for the code words, and we call this kind of coding as variable length coding. Okay, this is one popular way of coding, source coding really. So what is done, depending on some criterion, you can guess after some time what is that criterion really. We assign code words, say one code word for x1, another code word for x2, etc. And if necessary, the code word length, the number of bits for x1, number of bits for x2 may be different, okay, and that's known as variable length coding scheme. Now, if nk is the length of a code word of a letter xk, length of the code word representing xk, then I can come out with an average length of the code word n bar simply by this. Check this expression, is it not correct? A letter xk has a probability of p of xk of occurrence, okay, and if the length of code word which I am assigning to xk is nk, then I sum over all the probabilities over all the letters from 1 k equal to 1 to capital K, and what I get is the average length in terms of binary digits, okay, of a code word for one letter of that discrete memoryless source. Fine. Now, the source, how is it behaving? The source is generating one letter after another, is it not? If I now try to relate our information source to a physical situation, the information source being a discrete source, as if we will go on generating one letter after another, x1, x5 or x3, x5, x7, x9, x1, x2, x2, and like that in a random sequence, okay, with probabilities for each of these letters. And now we have decided to encode each letter by a group of binary bits, okay. The length of or the number of binary digits we are considering for representing a letter need not be same, so that we are talking about an average length of a code word, okay. Now, if you try to imagine how we can, I have given different representation to different letters and they are all coming one after another. So, ultimately this results in a binary sequence, binary bit stream, random ones and zeros, is it not? Now, how are we going to distinguish whether this group of 3 bits mean one letter or another group of 4 bits means another letter? Is it not a practical problem? There is an issue of distinction basically, okay. This issue is known as sorry that of unique decodability of the coding scheme. I must come out with a source coding scheme such that we are able to recover the corresponding code words unambiguously without any ambiguity, so that we can map them back to the letters x1, x2, x3, because if the information source gives me x1, x2, x3, I must deliver x1, x2, x3 to the information sink at the receiver end. So, the code words must be so designed so that they are uniquely decodable down the stream somewhere in the receiver when we have to convert them back to letters ultimately in the information sink, okay. So, any arbitrary coding is not going to help us really. A quick example here before we stop is that consider a small source alphabet with 4 letters A1, A2, A3, A4, isn't it? It's a small alphabet with 4 possibilities, okay, not a binary of course. And suppose arbitrarily that the probability of occurrence of A1, here I am indicated the letters as A1, I could also do it as x1, x2, I mean, or x1, x2, x3, x4, either way, okay, and let the probabilities be like this. We can quickly see that the sum of this probability must be 1, isn't it? We are talking about, we are using statistical theory really, so the probability would sum up to 1 really. Now, one coding scheme, suppose I have suggested like this. I have learnt about some variable length coding, so I have used different code word length. Code word length here is 1, 1, 2, 2, and suppose I have assigned these these bits accordingly for these letters x1, x2, x3, x4. Okay. In another scheme, I have assigned them like this. In a third scheme, I have assigned like this. Just think a little bit and let me know if you find any problem with this first scheme. It's not uniquely decodable, isn't it? Okay, because there is some problem. If I get 0, 0 out, you not know whether it's A1 or A3, 2 A1s coming one after another or A3. Very simple. So, there has been one condition for any good source coding scheme, one condition of unique decodability has to be followed, and for that many of the good codes, they follow one condition which is known as prefix conditioning. Prefix, yes, a prefix condition at the top you will find. A prefix condition code means this issue is considered appropriately, so that this ambiguity is no more there after when the source coding is done. Okay. The second code is an example of a prefix condition code. The prefix condition code is a code, means coding scheme, okay, in which no code word as a representation of the source letters is the prefix of any other code word. Check in this scheme that I have assigned 0 to this, okay, no other code word starts with 0. I have assigned 10 to x2, 10 does not appear anywhere. Okay, I have assigned 110 here. Just check that you cannot get 110 as any combination of a1 and a2, so that there is any ambiguity. So actually there is no ambiguity. Okay, and if I get a running stream of ones and zeros now following this coding style, I can distinguish what is what. As a quick example, I have a sequence here 0 1 1 1 0 0. Okay, this is uniquely decodable as a1 a4 a2 a1. Check for yourself. Okay, as an example, I have considered a third scheme which is not a prefix condition code, not a prefix condition code, but is still a uniquely decodable code. So it is not that all uniquely decodable codes are prefix condition codes, but all prefix condition codes are uniquely decodable codes, and there is a lot of theory and theorems, properties, etc. developed based on this prefix conditioning, because prefix conditioning is a regular structure, can be given shape and can be defined for necessary cases. Really. The Huffman code that we will take up in the next class is a kind of prefix condition code, prefix condition variable length source coding scheme. Okay. Any question at this point? Yes. Any question? Yes. Yes.
0 and 0 like the 0 0 1. Sir, for a 0 it will take the decode as A1, and if the next 0 comes, then what will it take?
See, if the next 0 comes, see all codes start with 0. So it will, when it finds 1, okay, after this next 0 it will not decide only after receiving 1 bit only. With delay in decision you can resolve this ambiguity. See, a 1 follows with 0, then the first 0 cannot be interpreted as the first one for x1. Okay. So ambiguity can be resolved in this case also. Okay. Any other question? Thank you.